Saturn did not choose to save us. We did not choose to be saved. But somewhere between that accident and this moment, we became the only thing in the universe that looked back and said, "Thank you. You are breathing right now, not because you decided to, because your lungs have been doing it since before you had a name, a reflex so ancient and automatic that your conscious mind has never once been in charge of it. You are breathing because 4.5 billion years of consequence led, step by step, to this exact moment, this room, this voice, this body, this air. But here is what nobody told you. The chain of consequence that produced you, the specific, improbable sequence of events without which none of this exists, depends on a planet you have never visited, a planet you cannot reach, a planet that does not know you are alive. You have seen pictures of it. You have probably called it beautiful. You have never once considered what it did for you. Today, you will. What I am about to share with you is not in most science textbooks, not because it is secret, but because it is too large to feel real until someone walks you through it slowly, piece by piece, and shows you what it means. It requires you to hold two ideas at the same time. The first, the universe is indifferent. It does not care whether you live or die, whether this planet survives or burns, whether any arrangement of matter ever becomes conscious enough to ask why it exists. The second, you have a very specific, very concrete reason for being alive today. And that reason is orbiting the sun 900 million miles from where you are sitting. And if that sounds like a contradiction, good. The best truths always do. So let us start at the beginning. Not the beginning of Earth, not the beginning of life. The beginning of the story that made both of those possible. A story that starts with a planet that was heading somewhere it had no business going, and another planet that stopped it, and the extraordinary thing that happened in the aftermath. Let us start with Saturn, with what it is, and with the 400 years we spent looking at it and seeing only the surface of the truth. What we thought we knew. Think of a painting that has hung in your house for 30 years. You pass it every morning. You no longer see it. You know it is there the way you know your own heartbeat is there, present, constant, unremarkable. Yet then one afternoon, a stranger stops in front of it and says very quietly, "Do you know what is on the other side of that canvas? Saturn is that painting." For 400 years, since Galileo turned his handmade telescope toward it in 1610, we have known that Saturn exists. We have seen it. We have mapped it, photographed it, sent spacecraft past it, built it into the iconography of science itself. It is the planet in the textbook diagram, the one next to the test tube and the DNA strand, when a magazine wants to say, "Here, this is what science looks like." We saw the rings. We called them rings. We put them in school curricula. We printed them on notebooks and coffee mugs and planetarium posters. We pointed at them with telescopes in backyard and said to our children, "That is Saturn, and those are its rings. And are they not something?" But we never asked what was on the other side of the canvas. Galileo and the failure of first sight. Galileo Galilei was not the kind of man who admitted confusion easily. He had spent his life arguing with the received wisdom of his age, measuring what everyone else simply accepted, refusing to treat authority as a substitute for evidence. And yet, when he turned his telescope towards Saturn in the summer of 1610, he wrote a letter to the Duke of Tuscany that could only be described as bewildered. The planet Saturn is not alone, but is composed of three, which almost touch one another and never move nor change with respect to one another. They are arranged in a line parallel to the zodiac, and the middle one is about 3 times the size of the lateral ones. He called them Saturn's ears, and he had no framework for rings, nothing in human experience or astronomy up to that moment prepared him to imagine a solid disk of material circling a planet in perfect alignment. So he saw three spheres. He described three spheres. He was completely, entirely wrong, and completely, entirely honest about his confusion. Then, in 1612, something stranger happened. The Earth passed through the plane of Saturn's rings. From our vantage point, the rings became edge-on, razor-thin, almost invisible. Saturn appeared quite suddenly to be alone. Galileo looked at his notes. He looked at the sky. He wrote, with a distress that is still palpable 4 centuries later, "I do not know what to say in a case so surprising, so unlooked for, oh, and so novel. A man who had overturned centuries of astronomical certainty, who had argued with the Pope, faced the Inquisition, published truths that powerful men wanted suppressed, looked at Saturn and admitted he had no words. The universe had shown him something he could not explain, and the most honest thing he could do was say so." In 1655, the Dutch astronomer Christian Huygens finally identified what Galileo had been looking at. He worked it out in secret for months, terrified of being wrong, before publishing his conclusion in a deliberately scrambled anagram to protect his priority while he continued to verify. When he finally announced it, "This is a ring," the response from the scientific community was not triumph but disbelief. A ring. How? Why? Of what? We still do not have complete answers to all of those questions. But we have learned, slowly and astonishingly, that the question we should have been asking all along was different. Not what are the rings, but what did Saturn do to this solar system, to this planet, to us, long before the rings existed? What Saturn actually is, let us be precise about scale, because scale is the thing that resists imagination until you anchor it to something the body already understands. Saturn is 9.5 times wider than Earth, not 9.5 times bigger, 9.5 times wider. In terms of volume, you could fit 764 Earths inside Saturn. Not stacked awkwardly, just fitted, the way you fill a jar with marbles. We're 764 of the only planet in the known universe that has ever harbored life, tucked inside a single gas giant that does not even rank as the largest in our solar system. And yet, for all that mass, for all that impossible, staggering bulk, Saturn is so diffuse, so composed of light gases rather than dense rock, that if you could somehow manufacture a bathtub large enough, Saturn would float. The most massive thing you will ever see with your naked eye from Earth, the ringed jewel of the solar system. It would bob on the surface of water like a child's toy. It spins so fast that it has distorted its own shape. Saturn is not a sphere. It is an oblate spheroid, flattened at the poles, bulging at the equator, and looking less like a planet and more like something that has been spinning so hard for so long that it has begun to lose its structural integrity. Its day is only 10.5 hours. Something that large, rotating that fast, creates forces that reshape matter. It sits 900 million miles from Earth on average. When light leaves Saturn, it travels for 80 minutes before reaching us. When Cassini, the spacecraft we sent there, transmitted a signal, that signal took 80 minutes to arrive. You could not have a conversation with something at Saturn. By the time your words arrived, the context would have changed. By the time the answer came back, you might have forgotten the question. This is the thing we called peaceful. This is the halo we put in textbooks to represent science. And we were looking at the surface of a mystery so deep that 400 years of observation had barely scratched it. And the mystery begins not with what Saturn is now, but with what it did before any of us existed to see it. The violence beneath the gold. Before we go back to the beginning, before we talk about what Saturn did to make this planet possible, you need to understand what Saturn actually is. Not the postcard version, the real thing. because everything that follows depends on you having a clear-eyed picture of this entity, not a beautiful planet, not a jewel, something older, stranger, and far more violent than anything the human imagination reliably produces when the word Saturn is spoken. The graveyard we call beautiful. The rings of Saturn are, without question, and the most visually stunning structure in our solar system. Nothing else comes close. Nothing else produces the same involuntary catch of breath when you see them through a good telescope for the first time. That moment of sheer visual disbelief when the eye refuses to accept that this is real, that something this elegant can exist in the cold indifference of space. They are also a crime scene. Here is what the rings actually are. They extend 282,000 kilometers from the planet, a span very close to the distance from Earth to the Moon, and yet in their main sections they are between 10 and 30 meters thick. 10 meters, the height of a 3-story building. Something that stretches nearly as far as the Moon and yet is no thicker than a modest house. They are not solid. They are not gold. They are billions of individual pieces of ice and rock, ranging from the size of a grain of sand to the size of a small mountain, all orbiting Saturn independently, all moving at different speeds depending on their distance from the planet, all colliding with each other constantly in a slow-motion catastrophe that has been happening for a very long time and will continue happening until the rings are gone. And they are going. The rings are dying. Saturn's gravity and magnetic field are pulling ring material down into the planet in a process called ring rain, a steady drizzle of charged, icy particles flowing along magnetic field lines into Saturn's atmosphere. The rate is staggering, between 0.4 and 3 metric tons per second. That is roughly 1 Olympic swimming pool worth of material every 15 minutes, and disappearing into the planet forever. At that rate, the rings have somewhere between 100 million and 300 million years left. In cosmic time, that is nothing, barely 2% of the age of the solar system. In human time, it is incomprehensible. But the point is this: we arrived just in time to see them. The window was narrow. We got lucky. Chrysalis, the moon Saturn killed. Where did the rings come from? For most of the history of astronomy, this was treated as an open question with several plausible answers and no decisive evidence for any of them. Then, in 2022, a team of researchers at MIT and the University of California published a paper in the journal Science that offered the most compelling explanation yet. And it was, at its heart, a story of murder. They called the victim Chrysalis. Chrysalis was a moon. The researchers calculated it was roughly the size of Iapetus, Saturn's third largest surviving moon, which means it was a world of substantial size, a body that had existed in stable orbit around Saturn for billions of years. It had survived the late heavy bombardment, the period roughly 4 billion years ago when the inner solar system was pelted by asteroids and comets in a cascade of destruction that reshaped every rocky world. It had survived intact and orbiting faithfully through eons of time that dwarfed the entire existence of complex life on Earth. And then something went wrong. The researchers' model suggests that gravitational interactions with Titan, Saturn's largest moon, gradually destabilized Chrysalis's orbit over millions of years. Slowly, incrementally, and in ways that would have been impossible to detect from outside the system, Chrysalis began drifting inward, closer to Saturn, closer to the point of no return. No witness existed, no consciousness recorded the approach. Chrysalis had no way of knowing that the gravitational equilibrium it had maintained for billions of years was failing, that the invisible mathematics of orbital mechanics had quietly, incrementally shifted against it. There was no warning. There was no final moment of recognition. There was only the physics, the tidal forces of a planet 95 times the mass of Earth pulling harder on one side of the moon than the other. until the difference exceeded the strength of the rock and ice that held the moon together. And then, not with a sound, because there is no sound in space, but with a visual violence that would have been unimaginable from Earth had anyone been alive to see it, Chrysalis came apart. 99% of it was swallowed by Saturn, dissolved into the atmosphere of the planet that had pulled it apart. The remaining 1%, the fragments too scattered and small to fall inward immediately, spread along the orbital plane and began the slow, grinding process of collision and fracture that, over millions of years, produced the structure we now see and call beautiful. The rings of Saturn are the scattered remnants of a world that ceased to exist approximately 160 million years ago, during the Jurassic period, when large dinosaurs were moving across the land masses of Earth, when the first birds were learning to fly, and when nothing on this planet had a concept of Saturn or a word for beauty, or a capacity to look up and feel wonder. We are looking at a graveyard. We have always been looking at a graveyard. We called it the most beautiful thing in the solar system. The geometry of rage, Saturn's hexagon. If the rings represent Saturn's past, the evidence of its violence, then the North Pole represents its present, and the North Pole does something that should not be possible. Imagine walking into a cathedral and finding, carved into the stone floor, a perfect geometric shape. 6 sides, each one exactly equal, meeting at perfect angles. The whole structure so precise and symmetrical that your first instinct is to look for the hand that made it. Not nature, a hand. Because nature does not make perfect hexagons. Fluid dynamics produces circles and spirals. Physics produces curves. Geometry in the wild is the product of intent. And yet there it is. At Saturn's North Pole, there has been spinning, without pause, without decay, without any sign of weakening. A 6-sided storm, the size of which makes the word storm feel inadequate. Each side of the hexagon is 14,500 kilometers long. That is longer than the diameter of Earth. The entire structure, from edge to edge, is 30,000 kilometers across. Wide enough to swallow 4 Earths and still have room. The winds along the hexagon's edges reach 320 kilometers per hour. That is more than double the wind speed of the strongest hurricane ever recorded on Earth. The storm extends 300 kilometers deep into Saturn's atmosphere, and at its center, at the exact geometric heart of this impossible 6-sided vortex, sits an eye. A hurricane-like vortex 50 times larger than a typical terrestrial storm, staring upward into space with a stillness that seems almost deliberate. The hexagon was first photographed by the Voyager spacecraft in 1981. Scientists assumed it was transient, a temporary weather pattern that would dissipate as Saturn's seasons changed. Saturn's seasons last 7 Earth years each, meaning 1 Saturnian year is roughly 30 Earth years. When the Cassini spacecraft arrived in 2004, more than 20 years after the first photographs, the hexagon was still there. When Cassini ended its mission in 2017, it was still there. It has now been observed continuously and without interruption for more than 40 years, and it shows no signs of stopping. Between 2006 and 2016, it changed color, from a deep blue to a golden hue. Scientists believe this may be related to seasonal changes in atmospheric chemistry as sunlight returned to the North Polar region. The hexagon itself is not a physical structure. It is a pattern, a standing wave in Saturn's atmosphere, maintained by the interaction of smaller vortices surrounding a larger eastward jet stream, each element pinching and constraining the others into a shape that emerges from pure physics. No one built it. No one sustains it. It simply is, the way mathematics simply is, inevitable once the conditions are right, indifferent to whether anyone is watching. Saturn does not know it is producing this shape. Order in the universe is not the product of intention. It is what happens when the right forces meet in the right configuration and neither yields. What looks like design is the shadow of constraint. Saturn is violent. Saturn is ancient. Saturn holds its storms for decades and wears its dead moons as rings. But none of this, not the graveyard of Chrysalis, not the geometric rage of the hexagon, not the radio emissions screaming into the dark, is why Saturn matters to you. Why Saturn matters to you requires going back, all the way back, to the beginning of this solar system, to a moment when everything that currently exists was still undecided. The crime scene at the beginning of time, 4.5 billion years ago, there was no Saturn. There was no Earth. There was no Sun, not yet in its current form. There was a cloud of gas and dust, the remnant of an older star that had lived its life and died, seeding the galaxy with the raw materials of everything that would come after. And in this cloud, something began. Gravity pulled. Small concentrations of mass attracted more mass. The cloud began to collapse inward, slowly at first, then faster, most of the material flowing toward the center and igniting into the star we call the Sun. The remainder, a thin disk of gas and dust still orbiting the newborn star, began its own process of accumulation. Particles clumped together, clumps merged into larger bodies. Larger bodies swept their orbits clean, pulling in everything within gravitational reach, growing into what we now call planets. This process took millions of years. And during those millions of years, nothing about the final arrangement was guaranteed. The planets did not form where they ended up. They formed in chaos and arrived at their current positions through a series of events so specific, so contingent on particular initial conditions, that astronomers now believe a solar system like ours, with the right planets in the right places maintaining the right orbits, may be genuinely rare in the galaxy. The wandering giants think of a construction site, not the finished building, the process, the ground still unstable, heavy machinery moving through spaces that will eventually be walls and floors and rooms. Anyone standing in the path of that machinery at the wrong moment does not survive to see the building completed. The early solar system was that construction site, and the machinery, the heavy, indifferent, gravitationally dominant machinery, was the gas giants. Jupiter formed first, and it formed large. Within a few million years of the Sun's ignition, Jupiter had swept up enough material to become roughly the mass it is today. A planet so massive that all the other planets in the solar system combined do not equal its bulk. Jupiter is not merely large in the way that the largest buildings are large. Jupiter is large in the way that changes the rules. A planet of Jupiter's mass does not simply orbit, it dominates. Everything within its gravitational reach is either captured, redirected, or expelled. And Jupiter was not staying put. In the early solar system, giant planets do not simply form and remain stationary. They interact with the gas disk from which they emerge. And that interaction creates forces that cause them to migrate. Jupiter, according to our best current models, formed in the region of space where the asteroid belt now exists, roughly 3.5 astronomical units from the Sun, and then it began to move inward. Pulled by the dynamics of the gas disk, drawn toward the warmer, denser interior of the forming solar system, Jupiter began a slow but inexorable drift toward the Sun. As it moved, it swept through the regions where the inner planets would eventually form. It scattered material. It ejected bodies from the system entirely. It compressed and redistributed the raw ingredients of planet formation in ways that should have been catastrophic for everything smaller than itself, which, in a solar system dominated by a single supermassive gas giant migrating inward, meant everything. Models of solar systems without a Saturn analog Systems where a Jupiter-like planet migrates inward without being stopped show an inner solar system radically different from ours. Earth-sized worlds form, but not in the habitable zone. The conditions for liquid water, for the chemistry that produces life, for the stable long-term orbital arrangement that allows billions of years of biological evolution, these conditions do not emerge. The system produces something, but not something like us. Jupiter was heading inward. The inner solar system, where Earth would one day form, was in its path. The raw materials that would eventually become you, the orbital position that would eventually be called home, the distance from the sun that made water liquid rather than ice or steam. All of this was in the path of the largest planet in the solar system, and it was moving in the wrong direction. Nothing at that moment in the history of this solar system was guaranteed to survive. Everything depended on what happened next. And what happened next was Saturn. The Grand Tack. Before we get to what actually happened, I want you to hold a picture in your mind. A runaway truck. No driver. No brakes. Rolling down a mountain road, gaining speed, carrying enough momentum to destroy everything at the bottom. There is nothing in its path that can absorb that impact, nothing small enough to stop it, nothing positioned to redirect it. And then from a side road something appears, not a rescue vehicle, not a barrier that was deliberately placed. Just another truck arriving at the intersection at exactly the right moment, at exactly the right speed, from exactly the right direction. And the physics of their interaction does what no single object could have accomplished. The first truck is stopped, redirected, sent back the way it came. Nobody planned it, nobody orchestrated it. The laws of physics did not care about the outcome. It happened because two massive objects arrived at the same place at the same time, and their mutual gravitational interaction produced a result that neither of them intended and neither of them could have avoided. That is what Saturn did to Jupiter. That is the Grand Tack. How it worked: Saturn formed after Jupiter, and it formed smaller, roughly a third of Jupiter's mass. But being smaller meant that Saturn moved through the protoplanetary disk faster than its larger neighbor. While Jupiter was migrating inward, sweeping through the region of the asteroid belt, heading toward the inner solar system, Saturn was forming behind it and beginning its own inward migration. And Saturn was catching up. The critical moment came when Saturn closed the distance enough to enter what physicists call a mean motion resonance with Jupiter. The specific resonance was a 3-to-2. For every 3 orbits Jupiter completed around the Sun, Saturn completed exactly 2. These numbers are not coincidental. They are the product of gravitational mathematics, the specific ratio at which the combined gravitational tugs of 2 planets begin to reinforce each other at regular, are repeating intervals rather than cancelling each other out at random. When 2 massive planets enter resonance, their combined gravitational influence exceeds the sum of their individual parts. The gas in the disk between them, the gas that had been pulling Jupiter inward, sustaining its migration, was expelled from that region. The force that had been driving Jupiter toward the Sun was neutralized. And then, and this is the pivot on which the entire subsequent history of the inner solar system turns, the same gravitational interaction that expelled the gas began to push both planets outward instead of inward. Jupiter stopped, turned, and moved away from the Sun, taking Saturn with it. The technical term for this reversal is a tack, borrowed from sailing, where a tack describes the moment when a boat turns into the wind and changes its direction of travel. In the Grand Tack model, Jupiter reached approximately 1.5 astronomical units from the Sun, roughly where Mars orbits today, before turning around and migrating back outward to something close to its current position at 5.25 astronomical units. Saturn migrated with it. The whole process, inward migration, resonance lock, reversal, outward migration took hundreds of thousands of years, perhaps 1 million years. In solar system time, that is the blink of an eye. In the consequences it produced, it was everything. What the tack made possible. The first consequence was immediate. Jupiter's inward migration had swept through the region of the asteroid belt twice, once going in, once going out. This double crossing, combined with the gravitational resonances that persisted after the planets reached their current positions, produced the asteroid belt we have today, a region of space that contains vastly less material than it started with, distributed in a specific pattern that reflects the two passages of the giant planets. Among the material that the double crossing redistributed were water-bearing asteroids, carbonaceous chondrites, primitive rocky bodies that formed in the colder outer regions of the disk and incorporated water into their structure. Jupiter's outward migration scattered some of these bodies into the inner solar system. Some of them, over the next hundreds of millions of years, fell onto the growing Earth, the water in your body, the water that makes up 60% of what you are, the water in every cell, the water that your blood uses to carry oxygen to your brain. The water you drank this morning has a chemical signature that matches the water found in these outer belt asteroids. The isotopic ratios of hydrogen and oxygen tell a story, and the story is this. The water on Earth did not originate here. It was delivered, and the mechanism that delivered it was set in motion by Jupiter's migration and Saturn's intervention. You are, in a measurable and specific sense, made partly of water that Saturn helped put here. The second consequence was structural. With Jupiter no longer continuing inward, the material of the inner solar system, the dust and gas and planetesimals that would eventually become the terrestrial planets, was able to accumulate under more stable conditions. In the specific region where the material concentrated was inside approximately 1 astronomical unit from the Sun. Earth formed in that region. Venus formed in that region. Both of them accumulated enough mass to become substantial planets. Mars, which formed farther out, in a region that Jupiter had swept relatively clean during its inward pass, ended up smaller than the models of planet formation would otherwise predict. Mars today is roughly 1/10 of Earth's mass. If Jupiter had never migrated inward, Mars should be roughly the size of Earth or larger. The Mars problem, as astronomers have called it for decades, is one of the most persistent puzzles in planetary science. And the grand tack provides the most compelling explanation. Jupiter was there, and it took most of the material that Mars needed to grow. But Mars being small is not a tragedy. Mars being small means that its gravitational influence on Earth is proportionally smaller, which matters for the long-term stability of Earth's orbit. The specific size of Mars, the specific composition of the asteroid belt, the specific position of Earth in the habitable zone. All of these trace back, in the grand tack model, to the moment when Saturn caught up to Jupiter and the resonance lock reversed their direction of travel. The moment with no witnesses, there was no one to see it. No consciousness existed anywhere in the solar system. No camera, no instrument, no mind that could register what was happening. Two gas giants, moving through a disk of gas and dust, their gravitational fields intersecting and interacting in ways that obeyed only the laws of physics, laws that do not require witnesses, do not respond to the absence of an audience, do not need to be observed to operate. Jupiter turned, it moved. Slowly, over 1,000 centuries, it traveled back toward where it had started. The material of the inner disk, the raw material of worlds, was compressed and distributed into a new configuration. On a small, unremarkable patch of that inner disk, roughly 100 million miles from the Sun, a planet began to form. It would take another 50 million years to complete the process. Another billion years after that before its surface cooled enough for liquid water to persist. Another 500 million years before something that could be called life appeared in that water, and another 3.5 billion years before one species of life on one continent of that planet looked up at the night sky and saw a golden-ringed world hanging in the dark, and said, in the only language it possessed, "That is beautiful." They did not know. They could not have known. They looked at the thing that had made them possible, and they saw only the surface. They saw rings, and light, and distance. They did not see the physics. They did not see the intervention. They did not see the 4.5 billion years of consequence that connected the turning of that distant planet to the breath they drew as they looked up. They would spend 400 years learning to see it. And when they finally did, when they finally understood what Saturn had done, without intention, without awareness, or without any possible care about the result, they would do something that has no parallel anywhere else in the known universe. They would build a machine and send it there. The grand tack is a hypothesis, not a law. It is our best current explanation for a series of features of the solar system that resist simpler explanations. The size of Mars, the composition of the asteroid belt, the distribution of water in the inner planets. It is supported by simulations, constrained by observations, and debated by scientists who are working, as scientists do, toward a more complete picture. But here is what is not debated. Jupiter migrated. Saturn formed and migrated after it. The two planets interacted. The configuration of the inner solar system, including the size, position, and composition of Earth, reflects those interactions. And the water on this planet bears the chemical fingerprint of material from the outer solar system that was redistributed during that period. The chain of causation between Saturn and you is not a metaphor. It is not a poetic way of describing coincidence. It is, as nearly as our instruments and mathematics can determine, a physical reality. Saturn is in the chain, near the top of it, in a position that no other body in the solar system occupies. And Saturn was not finished. 4.5 billion years after the grand tack, it would do something else, something it could not have done without us, and something that may carry the most important question our species has ever asked. But first, it had a secret, small, white, quiet, hidden beneath ice. What Saturn is hiding. Imagine you are driving through a part of the country you have never been before. Late afternoon. The road is empty, the landscape unremarkable, flat fields, a grey sky, the kind of scenery that does not ask anything of you. And then, past a bend in the road, you see a house with the lights on. Warm light through the windows. The shadow of movement inside, a chair on the porch. You slow down. You look. You are not certain what you are seeing. You cannot prove anything from the road, but you cannot keep driving without at least trying to understand what is happening in that house. Enceladus is that house. The moon nobody expected. Enceladus is small. In a system dominated by Titan, a moon larger than the planet Mercury, Enceladus is easy to overlook. It is roughly 500 kilometers in diameter, which sounds substantial until you hold it against the context. That is smaller than the state of Arizona. It is a marble in a system of bowling balls. From a distance, it looks like a polished ball of white ice. Brilliant, almost unnaturally reflective, because its surface is composed of freshwater ice that has been continuously renewed. A surface so clean and new that it reflects nearly 100% of the sunlight that hits it. Scientifically, this was one of the first clues that something unusual was happening. A surface that old should not look that new. Something was replenishing it. When Cassini flew past Enceladus's south pole in 2005, it found the source. 4 long fractures in the ice, blue-tinted, parallel, running roughly from east to west across the southern polar region. Scientists named them tiger stripes. Damascus sulcus, Baghdad sulcus, Cairo sulcus, Alexandria sulcus. Old world names for features on a world no human had ever seen up close. From these fractures, Enceladus is erupting. Giant plumes of water vapor and ice particles shoot hundreds of kilometers into space at supersonic speeds. The material escapes Enceladus's weak gravity and disperses into orbit around Saturn, eventually forming Saturn's E-ring, a diffuse outer ring that, it turns out, is not ancient debris at all, but the ongoing exhalation of a living geological system. Saturn's outermost visible ring is made of the breath of a small moon. The moon that Saturn is slowly kneading with tidal forces, keeping warm, keeping active, keeping erupting. What is inside? Cassini flew through those plumes. It tasted them, running its instruments through the material as the spacecraft passed through the erupting columns at several kilometers per second. And what it found changed the way we think about where life might exist. Salt. The plumes contain sodium chloride, table salt, at concentrations consistent with water that has been in contact with rock for a long period of time. Salt in water interacting with rock suggests chemistry. It suggests a process. It suggests that beneath the ice of Enceladus there is not simply frozen water, but a liquid ocean that has been in contact with a rocky seafloor, dissolving minerals, creating gradients, sustaining reactions. Organic molecules. The plumes contain complex carbon-bearing compounds, molecules that on Earth are associated with the chemistry of life, or at least with the conditions that precede life. Fresh analysis of Cassini data, published in late 2025, identified new molecular species in the plume material. Aliphatic compounds, nitrogen-bearing and oxygen-bearing molecules that appear to originate from within the ocean, rather than from surface processes. The analysis confirmed something astrobiologists had suspected but needed to prove. The chemistry happening inside Enceladus is not a superficial effect of radiation on surface ice. It is coming from below. Hydrogen. In 2017, Cassini detected molecular hydrogen in the plumes, the specific kind of hydrogen that on Earth is produced by hydrothermal reactions, where water interacts with hot rock in the deep ocean. On Earth, this process, called serpentinization, is associated with hydrothermal vents, those strange chimneys on the ocean floor where superheated water rich in chemicals emerges into the cold, deep sea. And around those vents on Earth, in conditions that receive no sunlight, operating on chemical energy alone, life thrives. Entire ecosystems built on chemistry rather than photosynthesis, on heat from the interior of the Earth rather than light from the sun. Enceladus may have the same system: warm water, rocky seafloor, hydrothermal activity, organic chemistry, energy to drive reactions, time, enormous quantities of geological time for processes to develop. In November 2025, researchers at Oxford University published a study confirming something that overturned a previous assumption about Enceladus. The heat that sustains its internal ocean is not concentrated only at the South Pole, where the tiger stripes erupt. There is significant heat flow from the North Pole as well. The energy budget of Enceladus is balanced, inputs from Saturn's tidal heating matching outputs from the Moon's surface. The implication is significant. This is not a temporary state. The internal ocean of Enceladus has the thermal stability to persist for billions of years. Not millions, billions. Long enough for anything that chemistry might produce to have time to develop into something more complex. The question the numbers cannot answer. Let us be precise about what we know and what we do not know. We know Enceladus has a global liquid water ocean. We know this ocean has been in contact with a rocky seafloor. We know the plumes contain salt, organic molecules, and hydrogen consistent with hydrothermal processes. We know the thermal energy sustaining the system is stable on geological timescales. We know that on Earth, environments with these exact characteristics harbor life. We do not know whether Enceladus is inhabited. We have not sampled the ocean directly. We have tasted the plumes, and the plumes are suggestive, but they are not proof. The difference between having the right ingredients and actually having life is a difference we do not yet know how to calculate. We do not have a theory of abiogenesis reliable enough to tell us. Given these conditions over this much time, life is probable, or improbable, or certain. We simply do not know. But here is what the discovery of Enceladus's ocean changed. Before Cassini, the working assumption of astrobiology was that life, if it existed elsewhere, existed in places that looked like Earth, warm, near a star, on a rocky surface with liquid surface water. Enceladus forced a revision. It demonstrated that the conditions for life, the specific chemistry, the specific energy sources, the specific liquid water environment, could exist in a small ice moon a billion miles from the Sun, in permanent darkness, under 20 kilometers of frozen crust, squeezed by the tidal forces of a gas giant. The habitable zone, that conceptual band around a star where temperatures permit liquid water on a planetary surface, suddenly seemed too narrow, too limited by our own example, too dependent on the assumption that life needs sunlight because we need sunlight. Enceladus said, maybe not. Maybe there are other ways. 3 in the morning, a lab somewhere, fluorescent light. A researcher alone with a screen full of data, mass spectra from Cassini's final high-speed flyby through the plumes of Enceladus. The pass where the spacecraft was moving fast enough to fragment molecules in ways that exposed their internal structure rather than just their overall mass. The researcher runs the analysis, stops, runs it again, compares it to the known molecular signatures, picks up the phone and calls a colleague. 3 in the morning. The colleague answers immediately. People who work on this data are always a little bit waiting for the call. Come look at this. That is all that is said. No interpretation, no claim. Just, come look at this. Because there is something in the chemistry of a moon a billion miles away that looks like the precursor to something that, on Earth, always leads somewhere significant. Not life, not yet, not even close to proof, but the kind of chemistry that, on the one planet where we know life exists, is never found without life nearby. Come look at this. Saturn built the conditions for Enceladus's ocean. Saturn's tidal forces power the hydrothermal system that may be generating the chemistry that might, we do not know, we cannot yet say, but might, be supporting something alive. Saturn, without intent, may be sustaining 2 places where life exists in this solar system. And the only way to find out, the only way to get from might to know, was to send something we cared about to a place it could not survive forever. We went to Saturn looking for a planet to photograph. We found a question that changes the meaning of our solitude. And the only way to honor that question, to protect the possibility of the answer, was to make a sacrifice that had no precedent in the history of exploration. The machine we sent to die, there is a thing that human beings do that no other known entity in the universe does. We build representatives. When we cannot go somewhere, when the distance is too vast or the conditions too lethal or the fuel budget too impossible, we encode our curiosity into metal and silicon and plutonium. And we launch that encoding into the void, and we call the things we build by names, and we follow them with instruments, and when they are gone, we grieve. This is not rational behavior by the standards of a species concerned primarily with survival. You do not grieve for a probe. A probe is a machine. It does not feel the cold of space, does not experience the years of travel, does not know whether it has arrived or not. It executes instructions, it transmits data, it functions or it fails. And yet in September of 2017, in a room at NASA's Jet Propulsion Laboratory in Pasadena, California, dozens of people who had spent years, in some cases entire careers, working on a single spacecraft stood together and wept when its signal went silent. Boxes of tissues were passed around the room. Scientists with PhDs, engineers who had spent decades on the most exacting technical problems in the history of human spaceflight, held each other. Because something they loved was gone. What does it mean that we do this? What does it say about us that we send our hopes out into the solar system, encoded in metal, and then mourn their loss? The machine that changed everything. Cassini-Huygens was conceived in the 1980s, before the internet was a household word, before GPS navigation existed, before the smartphones in your pocket contained more computing power than the entire spacecraft. It was designed by hand, by engineers working with the constraints of technology that would seem primitive to a college student today, and built to operate autonomously in an environment where real-time communication with Earth was impossible. By the time Cassini arrived at Saturn in 2004, after 7 years of travel and a gravitational slingshot past Jupiter, it was already antiquated by the standards of the technology that had been developed since its launch. It did not matter. It worked. Over 13 years in orbit around Saturn, Cassini completed 293 orbits of the planet. It returned 453,048 images. It transmitted 635 gigabytes of scientific data. It discovered the ocean of Enceladus. It mapped the lakes of liquid methane on Titan. It studied the hexagonal storm at Saturn's North Pole through multiple seasons. It photographed the rings from angles and distances never before achieved. It found shepherd moons that were actively sculpting ring structures. It discovered new moons. It detected organic molecules. It changed fundamentally and permanently what human beings know about the outer solar system. In 2005, the Huygens probe, attached to Cassini since launch, separated and descended through the atmosphere of Titan, landing on its surface. It was the first landing in the outer solar system, the first time any human-built object had touched down more than one astronomical unit from the Sun. Huygens transmitted data for 72 minutes after landing, sitting on the surface of a world covered in hydrocarbon sand and liquid methane lakes, in conditions that would destroy any Earth-based electronics within minutes, sending home the first images of a landscape that looked eerily like certain coastal regions on Earth, but was made of entirely different materials. We sent a piece of ourselves to the surface of another world, and it kept talking until the battery died. The decision. By 2017, Cassini was running out of fuel. The mission had already been extended twice, from its original 4-year plan to 13 years of operation. The spacecraft was aging, and a specific problem had emerged that required a decision. Cassini had been built and launched before we knew about Enceladus's ocean, before we knew about the plumes, before we understood that some of Saturn's moons might harbor conditions hospitable to life. Now we knew, or at least strongly suspected, and that knowledge created an ethical problem. If Cassini was simply left to drift when its fuel ran out, it would eventually, over years or decades, drift into contact with one of Saturn's moons, possibly Enceladus, possibly Titan, and Cassini, despite everything we had done to sterilize it during construction, was built by humans in human environments. It carried, almost certainly, microorganisms. Earth life, dormant in the cold of space for years, potentially still viable, are potentially capable of surviving and reproducing in the warm liquid ocean under Enceladus's ice. If we allowed Cassini to contaminate Enceladus, and then, at some future date, we found what appeared to be life in Enceladus's ocean, we would never be certain whether it was native life or hitchhiker life. We would have destroyed, permanently and irreparably, one of the most important scientific questions we have ever asked. The decision was made to destroy Cassini instead, not to abandon it, not to point it away from the moons and let it drift into interstellar space, to aim it deliberately at Saturn's atmosphere and to use its final fuel to keep its antenna pointed at Earth for as long as possible as it fell, so that it could transmit data, atmospheric composition readings, from deeper in Saturn's clouds than any instrument had ever reached, until the heat and pressure tore it apart. We sacrificed a machine that had taken decades to build and billions of dollars to operate, a machine that had changed everything we understood about the outer solar system, in order to protect the possibility of an answer to a question we have not yet been able to ask properly. We gave up something we knew and loved to preserve something we have not yet found. The last signal on September 15, 2017, Cassini entered Saturn's atmosphere moving at 113,000 kilometers per hour. Small thrusters fired continuously, fighting the increasing atmospheric resistance, working to hold the antenna pointed toward Earth. The spacecraft was already destroying itself, friction and heat beginning to ablate the outer structures, and it was still working. Still transmitting, still doing its job. In the control room at JPL, engineers watched the signal on their monitors, a thin line representing the carrier wave from a spacecraft falling into a planet a billion miles away. The signal was clean. The data was flowing. Someone said, out loud, into the charged silence of the room, "Give me just a few more minutes of data." Cassini gave 30 seconds more than predicted. 30 seconds of atmospheric data from deeper inside Saturn's cloud tops than any instrument before it had reached. Data that scientists are still analyzing today. Data that began in the final moments of the spacecraft's existence to answer questions about Saturn's interior structure that could not have been answered any other way. Then the signal flatlined, first on one frequency band, then on another. The line on the monitor went horizontal. The room was quiet for a moment, the specific silence of people who know exactly what has happened and are not ready to put words to it. Earl Mays, the Cassini program manager, spoke. His voice was level, professional, and clearly held together by effort. "I'm going to call this the end of mission, project manager, off the net." The applause was muted. The embraces were long. The boxes of tissues continued to make their rounds. There is a detail worth pausing on. At the signal that ended in that room, the flat line that Mays acknowledged as the end of mission represented something that had actually happened 83 minutes earlier. Light from Saturn, moving at the maximum speed anything can move, takes 83 minutes to reach Earth. Cassini had already been gone for an hour and 23 minutes before the people who built it knew it was gone. They stood in the control room, applauding, holding each other, grieving a machine that had already ceased to exist long enough for a person to drive partway across a city. The grief was real. The machine was already gone. Both things were true simultaneously, and neither made the other less so. Joe Pitesky, a Cassini science planner who had worked on the mission for years, and said something after the signal ended that I think captures what was happening in that room better than any technical description could. "We can't go there ourselves, so we build a spacecraft and load it up with instruments, and then we put on our hopes and desires, and we send them there. We put on our hopes and desires, and we send them there." That is not an engineering statement. That is a statement about what it means to be a species that cannot accept the limits of its own reach, that insists on touching what it cannot physically touch, on knowing what it cannot directly observe, on being present in places where presence is impossible. Cassini is part of Saturn now. The atoms that made up its structure, The aluminum and titanium and gold of its instruments, in the exotic materials of its electronics, have dissolved into Saturn's atmosphere, mixing with the hydrogen and helium and trace compounds of a gas giant that has been there for 4.5 billion years. The first human-made object to ever touch Saturn is still there, and will be there, dispersed but present, long after every trace of human civilization on Earth has been erased by time. We built Cassini to go where we cannot go. We loaded it with our curiosity and our hopes and our best instruments. And when it was gone, we stood in a room 1 billion miles away and grieved. If that is what we do for a machine, what does it tell you about us? And what does it mean that we sent it to a planet that billions of years earlier had already done something for us that we could never repay? What it all means. You are breathing right now. We started there. We come back there. Because everything between those two moments, everything we have covered, everything we have followed from the construction site of the early solar system to the control room in Pasadena, leads back to that one simple, continuous, automatic fact. You are breathing. Your heart is beating. 60% of what you are is water, and the chain of causation that produced all of this has Saturn in it, near the top, doing something that required no awareness and no intention and no knowledge that you would ever exist to trace it back. Let us be honest about what we have established and what we have not. The grand tack is a hypothesis, a strong one, supported by simulations and observations, accepted by a significant portion of the planetary science community, capable of explaining features of the solar system that other models cannot. But it is not proven. Science is not in the business of proof. It is in the business of best current explanation. And this is our best current explanation for why Jupiter stopped, why Earth formed where it did, why water arrived in the inner solar system, why Mars is the size it is. It may be revised, it may be replaced. Future missions, future instruments, future data may force us to update the story. That is not a weakness. That is what the process looks like when it is working correctly. We are not less awed by the story because it might be amended. We are more awed because the process of amendment is itself part of what makes us extraordinary. The nature of the debt. What do you owe to something that saved you without knowing it saved you? What do you owe to a planet that, through the blind operation of physics, produced the conditions that allowed your species to exist? The question sounds absurd. You cannot be indebted to physics. Saturn does not have a ledger. Gravity does not issue invoices. There is no transaction, no contract, no relationship in any conventional sense between a gas giant and the creatures who have evolved on a third planet from the Sun to look up at it and feel wonder. And yet something happened between us and Saturn that is genuinely unlike anything else in the known universe. Not an accident exactly. Accidents are things that happen to someone. This was something that happened to matter, blind matter, and then produced a consequence that eventually became capable of knowing that it happened. The consequence that became capable of knowing is us. And the knowing changes things. Before we looked up and understood, the connection between Saturn and Earth was a physical fact with no observer. After we looked up and understood, after Cassini and the Grand Tack and the ocean of Enceladus, it became something else. Not a relationship exactly, not a bond, but a recognition. A one-sided recognition necessarily, because Saturn has no mind to recognize anything. But a recognition nonetheless, a naming of what was already true. What Saturn is now, Saturn is still there. The rings are still dying, shedding their material into the planet at the same relentless rate, one swimming pool every 15 minutes, at the clock on their existence ticking toward a conclusion that no living thing on Earth will survive to witness. In 100 million years, give or take, they will be gone. Saturn will be a gas giant without rings, indistinguishable at a distance from any of 10,000 other gas giants we have identified in the galaxy. But right now, in this specific, narrow window of cosmic time, this sliver of geological history so thin it barely registers against the age of the solar system, the rings are here, and so are we. The two facts coexist. The beauty of Saturn and the existence of the beings who can observe and name that beauty. These things have overlapped in time, and the overlap is not guaranteed forever, and it will not come again once it has passed. We live in the time of the rings. We are, in all probability, and the only beings in this solar system who know that. The only beings who can see them and understand what they are seeing. The only beings who know what made them and how long they have been dying and how much time remains. We are the only beings in this solar system who sent a spacecraft to study them, named their moons after ancient gods and giants, built instruments precise enough to taste the plumes of Enceladus, and wept when the mission ended. What it means to be us, we are not the largest thing in the solar system, not the oldest, not the strongest, not the fastest. In every measurable physical category, we are modest, a thin biological film on the surface of a medium-sized rocky planet, dependent on a temperature range so narrow that a shift of a few degrees in either direction would end us, on sustained by a star that will eventually consume us, orbiting at the edge of a galaxy among 400 billion other stars that do not know we exist. This is not a cause for despair. This is the context. Because within that context, within the indifference of physics and the enormity of scale and the certainty of eventual extinction, we are the arrangement of matter that asked, why? We are the arrangement of matter that looked at a gas giant a billion miles away and wanted to understand it. We are the arrangement of matter that built a machine, loaded it with our hopes, flew it across the solar system, and sacrificed it to protect a question. We are the arrangement of matter that discovered, after 400 years of looking, that the beautiful thing we had been admiring had done something for us that we could never have imagined, at a time when there was no us to imagine anything. We are the arrangement of matter that traces the water in its body back to a gravitational resonance between two gas giants 4.5 billion years ago, and does not take that fact lightly. The rings will be gone in 100 million years. The sun will expand and consume the inner solar system in 5 billion years. Everything that has ever happened on this planet, every life lived, every word written, every piece of music composed, every moment of grief or love or wonder, will eventually be erased by the indifference that produced it. The universe does not grant exceptions. But here, now, in the brief window of time when the rings are still here and we are still here, and the ocean of Enceladus is still waiting to tell us something, we can look up. We can understand. We can trace the threads back to their origins and stand in genuine, clear-eyed, non-sentimental wonder at the improbability of all of it. That is not nothing. That is, as far as we can determine, everything. Saturn spun its storms before there was an eye to see them. It wore its rings before there was a mind to name them beautiful. It pulled the orbits of planets into configurations that made other planets possible. And it did all of this without knowledge, without intention, without any awareness that something downstream of its gravity would eventually look up and ask why. We are that something. We are the part of the universe that knows it owes a debt it cannot repay. The part that sends machines to stand in for us at the threshold of impossible places. The part that names its lost explorers and grieves when the signal goes silent. The rings are dying. We are, in our own way, temporary. The window in which both of us exist at the same time, the window in which anything alive can look up at those rings and know what they are and what they cost, is narrowing every day, every year, every century, one swimming pool at a time. But it has not closed yet. And while it has not closed, while the rings are still here, and we are still here, and the ocean beneath the ice of a small moon is still keeping its secrets, and there are still questions worth protecting by sacrifice, we have work to do. Saturn did not choose to save us. We did not choose to be saved, but somewhere between that accident and this moment, we became the only thing in the universe that looked back and said, "Thank you."